In the first lecture, we looked at only isomers of coordination compounds. I kind of threw some naming at you, names of ligands, and so if you paid attention, you'll have a much easier time. And so now we're going to look at the nomenclature, the systematic naming of these compounds, which is important. And but I'm going to go through it rather quickly, so you're aware of the rules and understand them. But I'm going to not test you a whole lot on the naming here, right? So we have a complex that is not charged. It's all one name, no spaces. This can be one long name. If you have a charged complex, obviously your coordination sphere can have a positive or negative charge, then it needs a counter ion, and so we always put a space in between cations and anions when we name compounds. The two examples shown here, in the first example, we have the coordination sphere as the negatively charged complex, so there's a space between sodium, the counter ion, and its name. Again, you can just look at that already and pick it apart by amine, and we have a prefix, and we have another name of a ligand, and then finally the metal name. And so there's something going on here with the ending that's different. We'll address that in a second. Here as well, pentamine. By the way, you can leave this out. The two vowels behind after each other you can reduce. And then carbonato, and then finally cobalt and the oxidation number. But the point here is that we have a space in between the cation and the anion. So the order that we name ligand, we have ligands and metals to name, so we name the ligand first, and we list them alphabetically, and then if we have multiple of one kind, if we have two chloros, we name them dichloro, or three amines, then we name them triamine. And so you're familiar with all of those prefixes. They're standard. And if your ligand is their double and it has a prefix in the name, such as ethylene diamine here, right? So there's already a prefix used in the name. We use different prefixes to indicate that there's multiple of them. So, and we put it in parentheses, and then we give it, in this case, we have two ethylene diamines. So instead of diethylene diamine, we call that bis-ethylene diamine. And so here are some of the goofy names: tetrakis, pentakis, hexakis, heptakis. Chances are we'll have either bis or tris that we will encounter here. We can have neutral ligands. Neutral ligands usually get the name that we would call them if they were standalone, like trichlorophosphine. These are phosphines. Phosphines that are oxidation state 3 would be, so you have a lone pair here. They're great ligands. They're called phosphines, and so you should be able to name any phosphine, just like amines. You have the same naming scheme. You can alter those alkyl groups, whether it's triethylamine or methylethylbutylamine. You should be able to name those compounds. Same with phosphines. Triethylphosphine or triphenylphosphine, you should have no trouble naming these. Nitrogen and oxygen get named dinitrogen and dioxygen, just to make sure. Of course, we also have oxide and nitrite. We'll get to that in a minute. Then there are also phosphorus 3 compounds that are great Lewis bases called the phosphites. ITE phosphites have alkoxide groups attached to them, 3. And so again, you from organic chemistry, you can name these groups and should be able to name any kind of phosphite. Here's a couple more examples of ligand structures that you might encounter: pyridine, bipyridine, tripyridine, triethylamine, which we had on the other slide. Of course, this here is a chelating ligand, and so just as a reminder, if I ask you to use this for isomers, you can just abbreviate like this when you draw it out, but you should know what bipyridine is, and that it is a chelating ligand and can only coordinate in the cis mode. Monodentate ligand pyridine, that's just another amine. And then we have tripyridine, so 3 points of contact can encapsulate. And so this can go, because it's free to rotate. It's not like that 2,1,1 pyridinophane that's restricted to the facial coordination mode. This can also go meridial and facial at this two different coordination modes. So those are neutral ligands that again we would call this triethylamine if it was by itself in a bottle, and also as a ligand triethylamine. Then we have special neutral ligands, several of which we've already seen and named. So ammonia is called the amine with 2 M's. Water is aqua. And then we have carbonyl here. Those are the 3 we've seen. The carbon monoxide is a carbonyl. And then we also have nitrogen monoxide is nitrosyl chloride. Nitrosyl chloride is a radical, so we'll take a look at that in the next chapter. And then we have carbon sulfide, which we call thiocarbonyl. Right? It's kind of like it binds the same way carbonyl does, except it has a thio group where the oxygen is replaced with the sulfur. It's the same chemical structure and bonding. Carbonyl is by far more common than a thiocarbonyl. Nevertheless, it needed to be mentioned. Then we have ionic ligands. Most ionic ligands, we just replace the name of the ion with an O. So nitride IDE, which is a single element that's charged. So we know the charge, 3-, that's predetermined. Just turns into nitrido, nitrite ITE, and then there's nitrate. Both would turn into nitrito and nitrato. So if you're ever in doubt if it's a special name or not, so just use the O name ending, right? Acetate turns into acetato, sulfite into sulfito. And of course I need to point out that nitrite is can coordinate either through nitrogen or oxygen. So this is a kappa here. When we name them, we indicate that with a kappa N or kappa O. If you have that information, if I just list the formula you don't know, just call it a nitrito. Here are some special anionic ligands: cyano, not cyanido, and fluoro, chloro, hydroxo. So all of those, fluoro, chloro, iodo, bromo, are named the same way we would for organic chemistry. And then it's not hydroxido, it's hydroxo, so there are some differences here. And then alkoxide groups are methoxo or butoxo type ligands. Then oxygen has several different coordination modes. If it's just O2-, single oxygen, it's just called oxo. Usually indicated here as a double bond, but we can have 2 different species, and we will look at those in detail at some other point. But this has a peroxide character, meaning that your oxidation state of each oxygen is not -2, it's going to be -1 and -1. So that's a different coordination mode. And then superoxo is different from oxide. It's a linear oxidation or coordination mode in this case here. All right. So organic groups, we give them, they are anionic sharp, so they're not really methyl groups, right? So if you have something in organic chemistry and you put a group on this long chain here, 1, 2, 3, 4, 5, 6, 7, so heptane, we call this methyl heptane. That methyl group is covalently bound to that carbon. It's not anionic, but a methyl group in the coordination sense they will be anionically charged, so that they are, so these are all have lone pair of electrons, not lone pairs, but they have 2 electron pairs, 1 electron pair, which then coordinates into those d orbitals, and so we give them the same name as we would alkyl groups from organic chemistry. So now to the metal. The metal always gets the oxidation state with Roman numerals, as you are used to from ionic naming of very simple compounds, iron 3 acetate, things like that. Copper 1 oxide, we always use the Roman numeral. And so if your coordination compound is either neutral or positively charged, then the metal name is just the name from the periodic table, so cobalt or iron or platinum. But if your coordination compound is negatively charged, as is the example here, right, because sodium is positively charged, and this amine trichloroplatinum compound has a negative charge, we call that platinate. It gets the ending ATE, and then the Roman numeral, of course, stays. So this would be sodium space amine trichloro and then platinate 2, right? Because each of these chloros has a -1 charge, which means this platinum has to be +2. So that's another thing you need to probably be able to do. We practiced that a while back, determining the charge of the metal based on the ligands that are attached. That's very important. Here are some examples of anionic names, or names of metals when they are part of an anionic complex. And so sometimes we use the Roman name here, or the Latin name: iron, copper, silver, and gold. We don't call it ironate, we call it ferrate, cuprate, argentate, or aurate. So there are those examples. And you know, maybe you've used the molybdate reagent before, and now you know why it was called molybdate, because it's anionically charged. If you are able to determine the isomer, if I draw a structure, you should also include that in your naming: cis or trans, mer, facial, or delta and lambda if they're optical isomers. Alright, so we also have bridging ligands. We saw this already. We use the symbol mu to indicate which ligand is bridging, but we would name it in the same fashion we just learned. You name all of the ligands of one complex, then the metal, and then you have this dash, mu dash, and the very next ligand name is going to be the bridging ligand, and then you continue naming as you would alphabetically with prefixes, and then finally space plus the counter ion. If you have a symmetrical complex, meaning if the two bridged complexes have the same chemical composition, like here we have a pentaamine chromium complex bridged by a hydroxyl ligand, we can lump this in together here, right? So we have pentaamine chromium 3 that is bridged, 2 of them, so we just call that bis pentaamine chromium 3, and then before the bis bridged complex, we in the beginning then say mu dash hydroxyl, indicating this hydroxyl group is bridging to coordination compounds that have the same chemical composition, and then space bromide. So how do I know this is chromium 3? Obviously my hydroxide is negatively charged. Each bromide is negatively charged, so we have a -6, and so you actually have the possibility of not having both of these being 3. You could have like 4 and 2, but it's unlikely, and since it is symmetrical, we just assign the equal oxidation states to both chromium ions. But that's something to keep in mind as you not just look at naming, also do more investigating and isomer drawing and things like that. The ambidentate ligands, which are the ones that can coordinate to different atoms, those are the two here, nitrite and nitrito. So this is a kappa. We basically call them the same, but we indicate which, we give it the same name. This is still thiocyanate. It's called a thiocyanato as a ligand, but if it coordinates through nitrogen, we just say kappa N or kappa S. Pretty simple here. And if there's another one that you've never seen, if you see kappa N on something, then you know it coordinates through the nitrogen, or whatever element is listed past that. It's possible that you have a coordination compound that is also a hydrate. These are named no differently than you would any hydrate. What you know, you've done this mono, di, tri, tetrahydrate. That's just water molecules sitting in the crystal structure. They're not coordinated to the iron in this case. And also sometimes it doesn't have to be a whole number, but it can also be 1.5 or 2.5. And so 1.5 happens to be sesquihydrate. So that's just a name that you are now familiar with. We are ready to practice. I have 6 formulas for you that we're going to come up with the compound. Of course, I can go the other way around, and it's up to you to practice. I have a few samples, and of course we have homework. So the first thing you want to do is you want to identify your ligands. So here we have this one here. Of course, that's the amine. Then we have the CO here, which is carbon monoxide. We call that a carbonyl. And then those are the ligand names. We put them in alphabetical order. They happen to be here. That's coincidental. That's for you to decide. And so then we also, if we want to determine the oxidation state of the metals, so we look at the charges of all of the counter ions as well as ligands. So both of those ligands are neutral. The chloride counter ion is negatively charged, and since there's just one, that means our cobalt's going to have a +1 charge, which makes this a cobalt 1. Obviously not 3. So we're going to call this a cobalt 1. So now we are ready to name this, and then of course the counter ion is just going to be called a chloride after we name this compound. So, and then we have 5 of the amines which get named first. So we have pentaamine, carbonyl, cobalt 1, space chloride. And so here it is. You can pick it apart. I already said you don't have to have pentaamine. I just kind of like to include it so that you can see all of the sections better, or at least I can see them better. Okay, so this is the first one. The next one I'm going to do by hand. It won't be as pretty, but we have aqua ligands, we have chloro ligands. So aqua is before chloro. They are neutral. These chloros are negatively charged, and then we have, it's going to be space chloride, and that's also negatively charged, and so we have 3 and 1, so this must be chromium 3. So now we put this all together. We have 4 aqua ligands, so it's going to be tetra aqua. I'm going to leave that out this time. Then di chloro, and finally chromium 3 space chloride. All right, moving on to the next one. So here we have potassium, space, and then we name the ligands followed by the oxidation state of the osmium here. Now this is a negatively charged complex, right? So if this is +1, we have 2 of them. This thing has a -2 charge, right? And so we're going to call this osmate. And we need a Roman numeral for that still, right? So let's go figure this out. We have chloroligands, and then this is nitride, right? It's a single nitrogen, so it's going to be nitride. Do, and then this is just chloro as a ligand. The chloros have a minus charge. The nitrogen also has a minus charge, but it's -3. So we have actually an overall -8 from these ligands here, right? We have 3 + 5, so that's -8. And then we have 2 cations, so that's +2, which leaves a -6 charge. So that must mean that osmium has a 6 charge. So we know this is osmium 6. And so now we can just name it. So the chloros are first, so space penta chloro nitrido osmate 4, and I lucked out here because this should all be one word, and there's a space here, and that is that. Moving on to the next one, this is a bridging ligand. These are not symmetrical, so we will name them one at a time. So we have the amine ligands, which are neutral. We have cyanoligands, which are negatively charged, and one of the cyanos is the bridging ligand. So that tells us that we have we should have cobalt 6 overall. So this is probably cobalt 3 and cobalt 3. And so now we can name that. We're just going to go from left to right. So we're going to call this pentaamine 2Ms cobalt 3, and then dash mu dash cyano, and then we keep going, penta cyano cobalt, and this should be one word. I'm running out, so I'll write it here. Cobalt also 3. This is neutral. No counter ions required in this case. So that's the name for this bridging complex. Here we have a cation and an anion. I expect you to be able to name this cation here. We have a nitrogen with 4 groups, which is an ammonium salt. If you think about, if you have any amine, whether it's ammonia or triethylamine or any amine, right? If you add hydrochloric acid to it or any kind of acid, what you're going to end up with is salt. So you're going to end up with ammonium chloride. And so the standalone cation we call ammonium. So this would be called tetramethyl ammonium. So that's our cation, tetramethyl ammonium space. We have, that's just one of them, right? So that's my cation. So that's important that I know that this has a positive charge when we are determining the oxidation state of the metal here, tungsten. And so this has a negative charge overall. So it's a tungstate. And we have simple carbonyl and chloroligands. The carbonyl comes first, so we have pentacarbonyl, and one chloro, so chloro. And this is going to be a tungstate, ATE. The question is, what is the charge of that tungsten, right? So if your counter ion is positively charged and your anion is negatively charged, your carbonyls are neutral, and you just have a -1 charge, your tungsten doesn't have a charge. It's tungsten 0. So the big problem here is, what's the Roman numeral for 0, right? So we're going to just call that tungstate 0. Okay. One last one. Here we have a chelating ligand called ethylene diamine. It is there twice, so we need to call this bis. Ethylene diamine. Diamine, just one M, right? And we don't know if it's cis or trans. Well, there's no such thing. In this case, they're both attached, so we don't have cis or trans. So forget that. Strike that from the record. Space. And then what is this thing called here? Oh, sorry, we need to do platinate. So, sorry, platinum. Platinum. And so the oxidation state, and then that's perchlorate. and perchlorate has a -1 charge. We have 2 of them. Ethylene diamine is neutral, so that means our platinum is platinum 2. So this is probably square planar, but because we don't have cis-trans, like I said. Okay, I think that's it. We can I can go through this, but I think it's pretty simple. Why don't you practice that to provide the name? I might give you a name and ask you to draw it, and so that might be more useful than me asking you to just name it, because you can ChatGPT that, right? Anyway, that's the end of this lecture, and most likely the quiz will be on isomers, heavy on the isomers. See you after spring break.